Okay, so here is going to be a quick run through the solutions to the Kirchhoff's laws practice. Probably it's going to take two videos because there's a lot of explanation, especially if you don't get it. Okay, so the first one, we have two different circuits. We want to figure out the currents through each resistor just using the junction rule. Okay, remember the junction rule is all about current into a junction equals a current out. It's kind of like a puzzle. It's not going to be a linear progression as you solve it. You have to look at what information is given and work from there. So here's our EMF source. Okay, they don't tell us what the value is, but we don't need it. We're not going to use Ohm's law here. We know there's 4 amps coming out, so there must be 4 amps going through R1. I'm not going to put the 4.0. And then so current is moving this way, and we get to a junction, and it splits. Some goes this way, some goes in this branch. Well, we can see that R6 has 1 amp, and R6 is connected in series to R4 and R5. In other words, they are all in a sequence, so they have to each have 1 amp. 1 amp, in other words, if 1 amp is coming into this, it meant that 1 amp had to come out of R4. Therefore, 1 amp had to come into R4. That means 1 amp went into that branch. 1 amp comes out of 6. That means 1 amp goes into 5. Now, you might be tempted to think that gives us 3 amps overall in this part of the branch. It is not. It's simply 1 amp. So if 1 amp went down this branch, that leaves, by the junction rule, 3 amps for that branch. So 4 come in, 1 and 3 go out. I got a 4 total. 3 comes out of here, 1's coming into this junction, 1 and 3 means 4, which we should expect because 4, 4, 4. So that's how you work that one out. All right, this one's just a little bit more, it's the same idea, just a little more complicated. Here's our EMF. We don't know the value, but we don't need to. I know 30 milliamps is coming out of here, so this is going to be 30. I also know that means 30 has to be coming into here. Okay? Now, things split. 40 goes out of here. I got 30 coming in. I've got 40 coming out of there. You might say, how can that be? Well, that means that this branch must have some coming in. If I get 40 going out, that means I have to have 40 coming in. 30 from this one, 10 from that one. So I have 10 here coming into this part, 30 here. Okay, so I'm going to go to what else? Another given. 200. So this is 200, and then 200's coming in to this junction. We already know 30 is going this branch, 10 went down this branch, leaving this branch with the difference between the two, which is 160. Therefore, R6 has 160. So I've got 160 coming in. I know I have 40 coming in, so that means I have to have 200. Right, 160 and 40 out of 200, and sure enough, that's consistent. Now, for number 2, we want to apply the loop rule for this circuit only. And I want to show how the loop rule actually works for 2 loops, the inner loop and then the outer loop here. Okay, so basically, let me draw a loop in a different color. All right, so our inner loop is this one, and that encompasses R1, R2, and R3. And we're told that the resistance is 2 ohms. So what I want to basically say is I want to say our EMF, that's our source, is equal to the drop across V1 plus V3 plus V2. And I'd calculate that each voltage is using Ohm's law. So R1 is 4. R1 is, they're all 2 ohms, but the amperage. So I got 4 times 2. There's the V1. V3 is 3 amps times 2 ohms plus 4 amps times 2 ohms. Add it all together, I get 22 volts. So I should get the same thing for the outer loop. The outer loop, I'm not going to sketch it, is 1, 4, 6, 5, and 2. Okay, so that's going to be, in fact, since 2 is a common element, I'm just going to pull that out. 2, that's my resistance, times each current. So 4 plus 1 plus 1 again, plus 1 again, plus 4. And if you add these up, you get 7 plus 4, 11. 2 times 11 is 22 volts, sure enough. And if you're paying attention, you'll see that this 1, 1, and 1 is the same as this 3 here, right? So we had 3 go down this branch, but we have only 1 amp in this branch, but since there's 3 drops, we get a total of essentially 6 volts overall. Okay, next problem. I've got an interesting looking circuit. I've got current coming out of here. It goes into here. It splits into 2 branches, then comes back to here, splits into 2 branches again, and then comes in. This is a combination of series and parallel. This is getting ahead of ourselves, but you might as well be familiar with this. These two are in parallel with each other. You can literally see that. But this whole thing, this block, is in series with this. Okay, so it asks, how does the sum of the currents in I1 and I2 compare to the sum of the currents in I3 and I4? And justify. Okay, so if I've got current coming into here, let's just call it, let's just say it's 100. Some's going to go here, some's going to go there. It has to split. It's not going to split evenly because they're not the same resistance. But when they come back together, I have to have 100 here, which means I have to have 100 going in, which splits a different way. So the answer is, how do they compare? They're the same. And your justification would be Kirchhoff's junction rule, okay, which I explained, but I'm just going to use shorthand, say this and that. Now it asks, how does the voltage drop for the 100 ohm compare to the voltage drop for the 250 ohm? Okay, so now we got to apply the loop rule. When we talk about voltage, it's the loop rule. And this one is, in one sense, easy to answer, but maybe a little bit more complicated to explain. So the answer is they're the same. And the simple answer for the reason for that is, anytime you have a parallel branches, the voltage drop must be the same for any branch, regardless of the resistance. Okay, what will be different for each branch is the amount of current. So this basically has low resistance but high current. This has high resistance and low current. In fact, this resistance is 2.5 times greater than that. Therefore, this is going to get 1 over 2.5 times the current. So when you multiply them, you're going to get the same voltage drop. The other way you could look at that is the loop rule, in that when I do a voltage drop across either one of these, it's going to be a certain amount. So the drop across here has to be the same as the drop across here, so they get the same total. All right, what does V1 plus V200 add up to? So if I take a loop that goes like this, where I just go through those two, the sum of this drop plus this drop has to add up to the overall EMF. That's what the loop rule is saying, so that's going to be 24 volts. Okay, because I can form a loop just of those two. Are the voltage drops of them equal? In other words, are these going to be 12 and 12? And the answer is no. Okay, why not? The simple answer is because the resistances are different, but actually it's a little bit more complicated than that, because I have to look at the other ones. So let me show you more mathematically. Okay, so the voltage drop across the 100 is equal to the current across the 100 times, sorry about that, times the resistance of that 100. And the voltage drop across the 200 is going to be equal to the current through the 200 times the resistance of the 200. So I basically have to show, are the product of these two going to be the same as the product of these two? And that's basically asking, is the current of the 100 over the current of the 200, is that ratio equal to 2? Because I'm looking to see if this gets twice, if this has half the resistance, does it get twice the current? Well, that's not going to be true, because the resistance of the 100 is not 1/2 the resistance of that. So if this is 2.5 times less resistance, it's going to get 2.5 more times current than this one. So the proportion of current that goes there is not going to be offset by that. All right, let's move on. I'm going to finish. Okay, so we've got statements about a circuit. So let's look at the circuit. We've got 2 loops. R1 is common to all of them, and then it splits, where we have 2 branches in the upper branch. We have R3 and R4 are part of one branch, and R2 is its own resistor in its own branch before they come back together here. Okay, it says 3 of the 4 students are correct, 1 is not. So let's take a look at Ali. He says I think the current in R1 will be the largest because all the current from the battery goes through it. That's absolutely correct, right? So if we got current coming out of the battery, it doesn't split when it goes in R1, so it gets all the current. These guys are going to get a fraction of the current because of the junction there. So Ali is correct. And the short answer is that is the junction rule. Okay, Ben, I think the current through R2, 3, and 4 will all be the same because there are two branches in a circuit and each branch will have half the current. He's right about that. There are two branches right here, one branch and one branch here, but they're not going to get the same current because the resistance of this branch is different than the resistance of this branch, because this branch is the sum of the resistances of those two, which is going to be different than that. So Ben is a no. So now we just got to show why Clyde and Dar are correct. He disagrees with Ben. Oh, that's good. I think R2 will be larger than the current in R3 and R4. The currents in the branches depend on the resistances. Yes. Okay, so Clyde is correct because of Ohm's law. Okay, so the voltage drop across this branch has to be the same as the voltage drop across that branch by the loop rule. This has a different resistance. In fact, it has less resistance than this upper branch, so it gets more current. And then Dar, we know is correct, but why? She says the only thing I am sure about is the current in R3 will be the same as R4 because they are in the same branch. Okay, so we don't know how much current goes up in R3, but we know it has to be the same as R4 because they're in series with one another by the junction rule. Okay, what goes into 3 must be the same as what goes out of 3, which must be the same as what goes into 4. All right, last one. We've got this complicated circuit with switches, and you got a bunch of combinations. Oh boy, and we got to see how many. So what does it ask? 8 possible switch figure sort of circuit. For each configuration, give the number of loops that have current going through at least one resistor. So I might not get through all this, but I'll get you started. Okay, so for A, situation A, everything is open, which is the default. So if I start right here, I'm going to start here. I'm going to ask how many different ways can I get to the positive, make a loop, and go through resistor. So if I want to go down this branch, I can't because it's open. Nothing happens. So I have to go this way through there, down through 2 resistors. And then I get a choice. I can't go down this branch because the switch is open. I can't go to this branch because the switch is open. So I'm only left with this one, which goes through 2 more. So there are 4 loops, or there are 4 resistors through which we can go. There's only one possible loop. Okay, now what changes in situation B? We close this guy. Okay, so nothing has changed here. We've got 1, 2. We can go through this 3. And we can go through these 2 still. So it looks like we have 5. Wait, oh, I'm sorry. What are we asking for? Oh, the number of loops that I'm sorry, I misinterpreted that. It goes through 4 resistors, but there's 1 loop in the previous one. So how many loops do we have? We have 1 loop, the original, and now we have another loop. So there's 2. Okay. Next. We are going to, let's see, open, closed, open. So this remains open. We're going to close S2 and 3 remains open. Alrighty, this is a little bit trickier. So we got to go through here and there's 1. Okay, and you might say 2. It's really tricky on this one. Here's the deal. Nothing is going to go through this loop. Why? Okay, so we got to go through these 2. We have no choice. But when we get to here, when we close 2, that's basically a short to get me directly to the positive. So there's no reason for any current to go up through these because they offer, and it's essentially an infinite resistance compared to this. So whenever you create a short in a branch, all the current's going to go through that short and bypass other branches. So technically there's only 1 in this one. And that's a tough one. Okay, let's see, next one. Now we have closed for 2 and 3. So this is closed and this is closed. So as before, even though this is closed, we're not going to go down to this branch because we have a short circuit in there. So that's going to be that one. In D, let's see, did I just do that? Just a D. So E1 is closed and these guys are open. This is probably the last one I'm going to be able to do. So just quickly, so this is closed. So we have a branch this way, right? And then we can also now go down this branch. So that looks like we have 2 loops. All right, let me quickly give the answer. So this is 4, 2, and 2 to let you work that out.